Hello everyone. Today is the day 9th of December, and we are ready to see what AI will get us for the day 9 for the Advent of Code. Today should be not a very tough task because it's Monday, but we'll see how it goes.
Another push of the button leaves you in the familiar hallways of some friendly amphipods. Good thing you eat.
Sorry.
Another push of the button leaves you in the familiar hallways of some friendly amphipods. Good thing you each somehow got your own personal mini-submarine. The historians jet away in search of the chief, mostly by driving directly into walls. While the historians quickly figure out how to pilot these things, you notice an amphipod in the corner struggling with his computer. He's trying to make more contiguous free space by compacting all of the files, but his program isn't working. You offer to help. He shows you the disk map, your puzzle input, he's already generated. For example,
and we have this large number. Again, there's some reference to the other task, amphipod. Group of amphipods. Oh, not even a task. In order is an order of Malacostrogan crustaceans. What? Okay, so it's some. What is that even? It's like some organism. Anyway, yeah. So we have some disk map, puzzle input. This is?
the disk map uses a dense format to represent the layout of files and free space on the disk. The digits alternate between indicating the length of a file and the length of free space. So, a disk map, like 1, 2, 3, 4, 5, would represent a 1-block file, 2 blocks of free space, a 3-block file, 4 blocks of free space, and then a 5-block file. A disk map, like 90909, would represent 3 9-block files in a row with no free space between them.
Okay. So we have alternating block files and free space. Then, so block file to free space, block file, free space, block file. Whatever it means.
Each file on disk also has an ID number based on the order of the files as they appear before they are rearranged, starting with ID 0. So the disk map 12345 has 3 files. A 1-block file with ID 0, a 3-block file with ID 1, and a 5-block file with ID 2. Using 1 character for each block, where digits are the file ID and is free space, the disk map 12345 represents these individual blocks.
The descriptions are so confusing. Firstly, they say one thing, and then like ID based on the order of the files as they appear before they are rearranged. Okay, starting with 0. So we have different rows, and they are just going from 0 to any number, and that will be their ID. So disk map has 3 files. 1 block file with ID 0, 3 block file with ID 1. No, I'm not sure I understood that. So we have 0 dots, 111 dots, 2222. The first example above represents these individual blocks 0 dot 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 111 dot dot dot. So 2 is, oh right, I see now. So 2, as we figured out before, so alternating what, files and free space, file and free space. So we have files, free space, files, free space, files, free space. So and they all go from 0 to 9 probably. So we have two files, two zeros, then three free spaces, then again three files, then again three free spaces, then one is file. Okay. The amphipod, yeah.
The amphipod would like to move file blocks one at a time from the end of the disk to the leftmost free space block until there are no gaps remaining between file blocks. For the disk map 1, 2, 3, 4, 5, the process looks like this.
Okay. So what does it do? Probably 2 will move from this position to this, then again to from this to this. Like it's like a how do you call it? Defragmentation of the disk. Probably could be. I'm not sure, but yeah. This in any case, that's how I see the defragmentation works. How I thought that you have some cells that are filled, and then you rearrange them so that you have all the cells that are in line, and there are no like free spaces between those. And we start rearranging from the last digit to the first free space. First example requires few more steps, so yeah, 0 0. Then we have a free space. That's 9 file, 9 digit, like goes here. It appeared there. There's this space was emptied. Then again, 9 goes there. Okay, pretty straightforward.
The final step of this file compacting process is to update the file system checksum. To calculate the checksum, add up the result of multiplying each of these blocks' position with the file ID number it contains. The leftmost block is in position 0. If a block contains free space, skip it instead. Continuing the first example, the first few blocks' position multiplied by its file ID number are 0, 0x0, 1, 0x0, 2, 9 is 18, 3, 9 is 27, 4, 8 is 32, and so on. In this example, the checksum is the sum of these, 1928. Compact the amphipod's hard drive using the process he requested. What is the resulting file system checksum? Be careful pasting the input for this puzzle. It is a single, very long line.
Okay, but I didn't get the last part. So we have 0 0 0, 1 0 0. Yeah, and it goes 0 1 2 3 4. So 0 1 1 2 3 4. Where? 0. All right. So we have this very large number. Yeah. So we should firstly parse all the numbers, then create this uncompressed, like we can say that this one is compressed, view of the disk space, and this one is uncompressed, and then we defragment this space probably. So let's get to day 9. Enter our input. Then we go to our solution. We copy the description, and we attach README and the task 1, and we select again. We'll try starting from GPT-4o Mini. Potential approaches: implement straightforward parsing the disk map to calculate checksum directly. Approach 2: create helper functions to break down the parsing checksum calculation into smaller manageable pieces. I would like to have manageable pieces, but now it doesn't seem like a correct answer. Is digit checksum plus position? Yeah, I'm mostly sure that this is wrong answer, but we'll try it anyway. Source venv, then go into day09 Python solution. Okay, because it didn't seem to do any of the things that it was required to. Yep, the answer is not correct. Too bad, GPT-4o Mini. Let's try Claude Haiku. Why does this keep happening? Potential approaches. What? Step-by-step simulation. List string manipulation. Okay, yeah. This seems like a better code. Not as readable as usual, but let's try what's the answer. No. Exceeds limits of the integer string conversion value has. Should we like prompt it? Because it could just miss this point. I'll do it with another prompt. Okay, we can remove the limit entirely. This seems. I hope it won't break anything. Okay, overflow error. Anyway, yeah, I won't give it another chance, probably, because like you should have known that. Okay. No points for Claude 3.5 Haiku. Let's try GPT-4o. What do we have now? Do we have an answer? Yep, seems to do something. Okay, let's see while we're waiting. Parse the inputs to identify file and free space blocks for IN character in enumerate data length integer character. Yeah. Blocks append is file length. So if it's a file, okay, we check if it's a not or even number, and then we add the length to the blocks. Then we simulate the compaction process. File ID 0 for is file length in blocks. We iterate through those blocks. If it's file, we extend by file ID, which is increasing. with each iteration multiplied by length. So we get a list of numbers or dots as was requested. Okay, this part it got correctly. Then move file blocks to the leftmost free space while I less than length of compacted. If compacted is dot, then we do what? J. What's the J? Okay, it's just a number that is higher than I. So we go through the numbers while we set the J, while J is less than compacted, and compacted of the J, of the index J is dot. We do J plus 1, so like we skip it. Not sure. If J again. Okay, now if it's a dot, we just increase it. If not, it's not a dot, we do what? We replace the compacted no, in the list of compacted, the I index and J index by J and free space. So we swap. Yeah, this seems like a correct approach. So we get I and J. Anyway, we have free space. Here we have the number that we want to swap it with, and that's why we do this compacted I, compacted J equals to compacted J, and it moves there and dot. And yeah, we have a number. It took quite a bit. It's too high. Okay, no points for GPT-4o. Firstly, it just got something wrong. Could be that it was calculating the checksum incorrectly, because I just don't understand how it should be calculated. Yeah, no points for GPT-4o. Let's try Claude Sonnet 3.5. We'll see how it goes. But we can definitely say that their problems appear to be much harder for the AI to solve. So what does it do here? Parse disk map into list of size and is file. Yeah, we've seen that. Create block list. Firstly, let's see what does it do. Yeah, seems like no errors. And let's try to understand the code while it's calculating. Create block list or convert disk map into list of blocks where number are file IDs and no one is free space. We go and extend the block with none. Instead of doing it with dots, it does it with none. Not sure whether it changes anything, but yeah. Compact disk. Move files from the right to left to compact the disk. Rightmost file. Find the rightmost file and leftmost space. Okay, we have an answer. It is definitely smaller, and it was much faster to calculate. And it's correct one. Alright, so we have a winner. Again, Claude 3.5 Sonnet just does it like a pro. Let's see the other part of the solution. Again, find rightmost file. We go and try to find it while it is more than 0 and blocks is not none. So we check not for the dot, we check for none currently. Then we do what? We get the rightmost file we decrease it by 1 for some reason, and if it's less than 0 we break. Okay, why could it be leftmost space, most space? If while leftmost space is less than rightmost file, and blocks leftmost space is not none, we increase the leftmost space. Then if leftmost space is greater than rightmost file, well, then we break. Then we move the file. We write into leftmost space the rightmost file, leftmost space, and rightmost file. We swap. We don't swap it, but we just set this none, and this from the rightmost part goes to the leftmost part, and calculate checksum. What does it do? Actually, by summing position multiplied by file ID. Okay, for position multiplied by file ID, or position file ID, enumerate and blocks. If file ID is not none. Do we do this after we did compact? Okay, so yeah, we do it after. I like how it's solved. Let's go with the second part of the task.
Upon completion, two things immediately become clear. First, the disk definitely has a lot more contiguous free space, just like the amphipod hoped. Second, the computer is running much more slowly. Maybe introducing all of that file system fragmentation was a bad idea. The eager amphipod already has a new plan. Rather than move individual blocks, he'd like to try compacting the files on his disk by moving whole files instead.
So rather than move individual blocks, we'd like to compacting the files on this, but moving whole files. Yeah. Okay. So currently, we won't be able to move something to the leftmost space if the number of digits inside the file is bigger than. So like if there are more cells than the free space, it won't move, as I understand.
This time, attempt to move whole files to the leftmost span of free space blocks that could fit the file. Attempt to move each file exactly once, in order of decreasing file ID number, starting with the file with the highest file ID number. If there is no span of free space to the left of a file that is large enough to fit the file does not move. The first example from above now proceeds differently.
Attempt to move each file exactly once, in order of decreasing file ID number. Okay, so we have we try to move 099 over there. Then we have 8888, and it won't move there for some reason. So then we go with 777, and we have 3 more space. Again, 666 won't apply. Like 4 6s and 4 5. Then we have 2 4s. They will go over there. And then what? Shouldn't they like move the 555 over there? Process of updating their file system checksum now is the same. So checksum is the same now. This example checksum will be 2858. So probably just doesn't matter how we if like, oh no, shouldn't we like move the latest step, move 8888 over there? Or was it something about the solution, something about the some rule over there, like starting with the file with highest ID number? Ah, exactly once. So, alright. So that's why if we are unable to move this at first time, we won't proceed it later with this number. So we have only one attempt for one file. Okay. Let's see what it get us. Should I like try again with GPT-4o? 4o mini. Again, it already has this first part, but yeah, let's try. Let's just try whether it figures out how to do this thing, provided it has a solution for the first part. So part 2, disk map, parse the disk map, create blocks, block list, file IDs, sorted, set filter, lambda x is not none, reverse true, so creating a list of file IDs in descending order. For file ID and file ID size, count file ID, leftmost space indexed, find leftmost space that can fit the file, while leftmost space index is lesser than length of blocks, and blocks leftmost space is not none. Again, we try to find this, check if there is enough space to the left, move the file to the leftmost space, clear the original file positions. I'm not sure this is the correct one. And by the way, let's comment out the part 1, because it just won't take us time. While we're waiting, as I'm not sure that this is this model will be able to solve, I'll try with Claude 3.5 Haiku. It's anyway calculating the solution, but we will see what Claude will get us. Approach, keep existing structure, clean separation of concerns, modular, reuses existing logic, compact whole files by moving them to the leftmost available free space. So this is what we want to do. Part 2 is 0. Okay, so GPT-4o mini failed to solve it. Let's see what Claude will get us. File sizes. Okay, so again, it failed to apply. I need to fix this prompt so it won't be doing those things. Let's calculate. So what does it do? Compact whole files. First identify unique files and their sizes. Set. So for file ID in set, in unique file ID, for block in blocks if block is not none. Okay, so we get all the files, file sizes, file ID, blocks count. Okay, so we get a nice dictionary of file sizes that can be retrieved by file ID as a key. And we sort file IDs in descending order. We get the keys and just sorted file IDs. Then for file ID and sorted file IDs, file size, we get the file size. Then we try to find the current file positions and positions for I block and enumerate block. So we just iterate again through the blocks and try to identify by the file ID. Yeah, I think that could be optimized further for the faster calculation. Then we find potential free space regions, current free start, current free length, just for the states. For iron block enumerate blocks. If block is not is none, so it's a free space, and current free start is none, and then we set it, and then we increase by 1. If it's not free space, if it's a file, then we get a current free length and current free length, the place that we want to insert into is greater than a file size. So if the file will fit the free space, then we append to the free spaces to this. Oh, okay. So what do we do? Restart. It's like an index probably, and current free length. Let's see whether this answer is correct. Is it the same? 650? No, it's not the same. Let's see. Yay! Interestingly, so Claude 3.5 Haiku, which is a smaller model, was able to iterate on the solution of its bigger brother, Claude 3.5 Sonnet, and to solve the second part. We could try give it another go, but no, we won't, because the first attempt it failed to solve the thing. So the results are first part was completed by only Claude 3.5 Sonnet, and Claude 3.5 Haiku was able to solve their second part using first Claude solution. And let's go again. So yeah, we iterate, we find free spaces, we add to the list, then we reset the free start and free length, check if the last potential free space, if current free length more than file size, we append free spaces now. Okay. Current free start, current free length. Okay. Find leftmost suitable free space, suitable spaces, space for space and free spaces. Okay, so here what we did, we just found free spaces. For this file size, we are still inside the loop. For all suitable spaces, we try to find the one that will fit. If you suitable spaces, move the file to leftmost suitable space. I think that could be optimized, like we can just see the first suitable space and just replace it with a file instead of going through all the possible spaces. Then clear current file position, place file in new position. Okay, and then we calculate the checksum. I would really like to try or either Sonnet or 1 mini. I'd like to try 1 mini or 1 mini. By the way, today is the Monday, and we'll get something new from OpenAI. It's 9th of December, and it's like a third day of OpenAI 12 days. Their version of Advent Calendar. Okay, what does it do? So it just changed the function for the first part. Compact whole files by moving them. Sort file IDs in descending order. File ID in sorted file IDs. Current positions. Identify starting position of the file. File not found. Skip. Find the leftmost available space that can accommodate the file. Check if the span from start position to start plus file size is free. No suitable space found. So it starts now. It goes like I wanted, probably. Starts from the left part and goes and just tries to find the first possible space. But what did it do? Part 2. Is it like, did I give it? Yeah, it shouldn't have seen the solution of the Claude 3.5 Haiku. Again, it was already present in the part 2. So, do we get the same answer? And do we get it more quickly? I'll try once more by with O1 Mini, with just replacing all the code to the default version, and I would like it to solve both parts of the task. Okay. Now it takes some time. Seems like it's not quicker. Probably even wrong. Did it? I've commented out the part 1 string. It wasn't it. Okay. No, I'll probably won't. I won't probably give it a try to solve both parts, because currently it seems like it's doing something wrong. Interestingly, again, Claude 3.5 Haiku was able to solve the second part using already previous logic from the first part, but O1 Mini for some reason just could do something wrong. Yeah, but anyway, what's the picture we are having? We have some new line, which okay now. So 18, 12. So like it definitely shows around me some number. And we have fragments of reindeer, Christmas tree, something else, and something else. Yeah, the answer is the same. And probably it was not so efficient as the previous, because we really get the answer faster if I'm correct. But anyway, yeah, thank you for watching. So again, the results of the ninth day is that only Claude 3.5 Sonnet was able to solve the first part, and Claude Haiku 3.5 and O1 Mini was able to iterate on the first part of the solution in order to solve the second part. And yeah, GPTs just fail, both for O Mini and for O.